All right, so we've successfully used a magnetic gradient to pick out one single 2D slice of tissue. That's a huge step. But that's all we have, a slice. We don't have an image yet. To actually build that picture, we need to talk about a really crucial process called frequency encoding.
So this is the big question, right? We've zapped the protons in our slice with some radio waves, and now they're all sending a signal back to our machine. The problem is, it's just one single jumbled up signal from the entire slice. How in the world do we turn that one stream of data into a detailed picture?
You can think of it like this. Right after our RF pulse, every single excited proton is spinning, or processing, at the exact same frequency. It's like having a massive choir where everyone is singing the exact same note. The signal we pick up is just one continuous wave. We know there's something there, but we have absolutely no idea where within the slice any of it is coming from.
And this right here is what we call the localization problem. We've got to find a way to tell the signals from the left side of the brain apart from the signals from the right side, or the top from the bottom. Without that spatial information, we can't build an image. It's just a signal.
Seriously, if we just took the signal as it is right now, we'd get one single data point, basically the average signal from the entire slice. And that's not an image, it's just a number. So the critical next step is to somehow bake that location information directly into the signal itself.
So how do we do it? Well, the answer once again comes from the incredibly clever use of magnetic field gradients. These are the exact tools that are going to let us systematically encode the location of our protons into the MR signal they're sending out. Just as a quick refresher, a gradient is just a weaker secondary magnetic field that we layer on top of our main, powerful B0 field. And the key thing to remember is that this gradient field isn't uniform. It actually changes the total magnetic field strength in a very predictable, linear way from one side of the scanner to the other.
And this is the fundamental principle of all MRI localization. We know from the Larmor equation, and this is super important, that the spinning frequency of a proton is directly tied to the strength of the magnetic field it's sitting in. So if we can make the magnetic field change predictably across our slice, we can make the frequencies of the protons change too. And just like that, location becomes tied to frequency.
We've actually already seen this in action, haven't we? For slice selection, we applied a gradient from head to toe along the z-axis. This made each slice of the body have its own unique resonant frequency, which let us excite just one of them with a perfectly tuned radio frequency pulse.
Okay, now for the really brilliant next step. After we've selected our slice, we turn on a second gradient. But this one is pointed in a different direction, say from left to right across the slice we just selected. This new gradient is our frequency encoding gradient.
We apply this new gradient at the exact same time that we're listening for the signal to come back, and its whole job is to stamp a unique frequency onto the signal based purely on its horizontal position.
This slide breaks it down perfectly. The gradient makes the magnetic field a little weaker on one side and a little stronger on the other. What happens? Well, the protons on the weaker side spin a bit slower, giving off a lower frequency signal. And the protons on the stronger side spin faster, giving off a higher frequency signal. It's that simple. We've just encoded left to right position into frequency. So, what does our receiver coil hear now? Instead of that one pure, simple note from our choir, it hears a total jumble. It's a really complex waveform that's basically the sum of all these new, different frequencies coming from every single column across the slice, all mashed together. Now, this complex signal might just look like noise, but it's actually packed with valuable information. We just need the right mathematical key to unlock it. And that key is an incredibly powerful tool called the Fourier transformation. I mean, this is the next big hurdle, right? Our machine has collected this incredibly complicated wave over a very short period of time. How can we possibly untangle that mess to figure out how much signal came from the far left, how much from the middle, and how much from the far right? This is where the Fourier transform comes to the rescue. The best way to think about it is like a prism for sound. You know how a prism takes white light and breaks it down into all the individual colors of the rainbow? Well, the Fourier transform does the same thing for our signal. It takes our complex wave and breaks it down into all the individual frequencies that were added together to make it. And, this is crucial, it also tells us the strength or amplitude of each of those frequencies. So the input to this mathematical machine is that raw, jumbled signal we just collected. We basically feed it a bunch of data points that show how the total signal strength changed over time.
And what pops out the other side is amazing. The Fourier transform gives us a graph, but instead of amplitude versus time, it's amplitude versus frequency. And because we were so clever about making frequency correspond to a specific location, this graph is actually a map of the signal strength for each and every column across our slice.
And there you have it. We've done it. We've successfully created a 1D projection of our slice. We now know how much signal is coming from each vertical column. We've solved the localization problem at least in one dimension. But an image isn't just a line, is it? It needs 2 dimensions. We've figured out the horizontal axis, but we still have 0 information about the vertical axis. And that's the final piece of this amazing imaging puzzle. Because our frequency encoding gradient only changed the field from left to right, all the protons in a single vertical column, like you see here with A, B, and C, are all sitting in the same magnetic field. They're all still singing the same note. We can't tell them apart. We know the total signal from that column, but we have no idea how it's distributed from top to bottom.
Now, this is a great question, and it's probably what a lot of you are thinking. It seems like the most obvious solution, doesn't it? Just design some kind of super gradient that varies not only left to right, but also top to bottom, so every single pixel gets its own unique frequency.
Well, the answer, unfortunately, is that physics just gets in the way. It is physically impossible to construct a magnetic field where every single point within a 2D plane or a 3D volume has its own unique field strength. It just can't be done. No matter how you try to design it, you'll always have multiple points sharing the same frequency.
This quote from the source material really says it all. This whole approach is, and I quote, not tenable. It's a fundamental physical limitation that we simply can't engineer our way around. So, MRI needs a different, and frankly, an even more clever trick to solve for that second dimension.
And that trick has a name: phase encoding. It's the incredibly clever method we use to tell pixels within the same column apart, to tell A from B from C. It's the key to building our final, complete, 2-dimensional image. But how that works, well, that's a fantastic story for our next explainer.